Okay, welcome you all for this session. In this session, we will solve some of the numerical problems on the damped vibrations. Okay, we will revise a bit. In the last sessions, we have seen that there are different types of systems are there: underdamped system, overdamped system, and critically damped system. We have seen the response for the various damped system. For the underdamped system, where the displacement, this is the displacement model, x is equal to e raised to minus zeta omega nt sine omega dt plus phi, where x is the amplitude, zeta is the damping ratio, omega n is the natural frequency, omega d is the damped natural frequency, and phi is the phase. Okay, where zeta is the damping ratio, c by cc. C is the actual coefficient, damping coefficient, cc is the critical damping coefficient. To find this cc, we are using 2m omega n, where omega n is equal to square root of k by m. To find omega d, omega n square root of 1 minus zeta square. Okay, these are the important formulas. These are very helpful in the solving numerical problems. Okay, this is the damped, this is the response for the underdamped system. It is oscillatory in motion or periodic. It is periodic. Only underdamped systems are periodic in nature. And this is logarithm decrement delta. It is denoted as delta, the ratio of two successive amplitudes. Delta is equal to 2 pi zeta divided by square root of 1 minus zeta square. If you know zeta value, that is damping ratio, then logarithmic decrement can be determined, or if you know delta, then zeta can be calculated. Okay, for one cycle, how much time it takes, that is the time period. To calculate the time period, we can use this formula, 2 pi divided by omega d, where omega d, again it is repeating, omega n square root of 1 minus zeta square. If you know mass and stiffness, then omega n can be calculated by omega n equal to square root of k by m. And zeta, how zeta can be calculated? C by cc, where cc is 2m omega n. For one cycle, it is xn divided by xn plus 1. For n number of cycle, we can use this equation. Okay, where delta is the logarithm decrement. We have two expressions to find the logarithm decrement here. Okay, for overdamped system, this is the response, and for critical damped system, this is the response. When it is plotted in a graph, okay, for different systems, this oscillatory in nature, it is underdamped system. For underdamped system, always zeta value is less than 1. If zeta is 1, then it is critically damped system. What is the difference between critically damped system and overdamped system? For overdamped system, zeta value is more than 1. Okay, for critically damped system, zeta value is exactly 1. If zeta is 1, the system comes to equilibrium position as quickly as possible. Okay, for overdamped system, it takes some time to come to equilibrium position. As the zeta value goes on bigger, it takes more time to come to the equilibrium. For example, if you take zeta equal to 2, it takes this much of time. For zeta equal to 5, okay, it takes this much of time. So as the zeta value goes on bigger or larger, then it takes more time. Okay, the time period equal to 2 pi divided by omega d. All the responses are plotted in a single figure here. Okay, let us solve the first problem. Okay, read this problem. Okay, let us solve the first problem. For the system shown in figure, the characteristics of the dashpot means it is damper, is such that when a constant force 60 Newton is applied to the piston, its velocity found to be constant at 0.12 meter per second. Okay, when you will get the data with respect to this damper, that is force and velocity, you use this equation and find damping coefficient. F is equal to Cx dot, where F is the damping force 60 Newton and x dot is the velocity 0.12. Okay, substituting force and x dot velocity, you will get a damping coefficient. For all the problems, or any problem, if you find damping force and velocity, you will get this damping coefficient. Okay, what is asked in this problem? Damping coefficient only. force is equal to Cx dot. Force is 60 Newton, it is given here, and initial velocity is 0.12 meter per second. So C value, that is damping coefficient 500 Newton second per. Then check whether the system is periodic or aperiodic. Periodic means only if the zeta value is less than 1 for underdamped system, only periodic. Critical damping and overdamping systems are aperiodic. Okay, for that you find zeta. If zeta is less than 1, then it is periodic. Okay, how to find zeta? Zeta equal to C by Cc. We have C value here 500. How to find Cc? 2m omega n. Mass is given in the figure 50 kg. Omega n can be calculated by square root of k by m. K value is 1500 divided by mass. Okay, C. Okay, now we have C and Cc value. Using this formula you find zeta value. Okay, it is 1.67. It is more than 1, so it is overdamped. Overdamped systems are aperiodic. So this is the first problem. Okay, let's start the second problem. In this problem, what are the given data are there? A body of mass 10 kg, mass is given, is suspended from a spring having a stiffness value 2 Newton per millimeter. You convert it to Newton per meters. So it is 2000 Newton per meters. Mass is given, stiffness is given. If mass and stiffness are given, then you can calculate omega n. Omega n is equal to square root of k by m. A damper having a resistance of 5 Newton at a velocity. I said earlier, if the force, damping force and velocity is given, then damping coefficient can be calculated using F is equal to Cx dot. This is F 5 Newtons, x dot is the velocity 0.1. F is equal to Cx dot, where C you find it by this equation. F is equal to Cx dot. Okay, so mass, stiffness and C, that is damping coefficient. Now we have these values. Using these three values, now you find ratio of successive amplitudes. Okay, this is underdamped system. This is the first amplitude, second amplitude, third amplitude, fourth amplitude. So he is asking what is the ratio of two amplitudes. What is x1 by x2 or x2 by x3? What is the ratio of successive amplitude? Okay, we know that now we need to find x1 by x2 or any two successive ratios of amplitude. Okay, for that you need to find delta value, that is logarithmic decrement. Okay, if you know zeta value, then logarithmic decrement can be calculated. How to find zeta? That is C by Cc. C value, it is calculated here 50 Newton per Newton second per meter, and Cc can be calculated by 2m omega n. So zeta value is 0.1768. If you substitute this zeta value in this expression, you will get a logarithmic decrement. Okay, logarithmic decrement expression for one cycle, it is also ln xn by xn plus 1. It is for one cycle. Okay, now ratio of successive amplitude means xn by xn plus 1. This delta value, it is this delta value by, if you know this zeta, this can be calculated. This value, calculated value is 1.12. Okay, this value is 1.12. So what is xn by xn plus 1? Xn by xn plus 1 is equal to e raised to delta. It is written here, e raised to delta. This value is 3.095. This is the ratio of the successive amplitude. Next, amplitude of the body after 10 cycles. This is one cycle. After 10 cycle, what is the amplitude? If the initial amplitude, if this initial amplitude is 15 mm. Okay, again we are using the same logarithmic decrement expression. This is for n cycle. Delta is equal to 1 by n ln x naught by xn. X naught is the initial amplitude. Okay, delta value, this delta value, it is 1.1286 for 10 number of cycles. First you find what is the ratio of x naught by xn. X naught is the initial and xn is the after 10 cycles. So this value, it is 79,698. Okay, you substitute this initial value, that is 15 mm. So by this you will get what is the amplitude after 10 cycles. Okay, we will continue the numerical problems again in the next video. Thank you.